Using the normal distribution to approximate other distributions, Part 2. Suppose fires are reported in a municipality under the conditions of a Poisson process with, on average, 1 fire every 12 hours. If there are more than 3 fires reported in any 24-hour day, we'll call this an external assistance day, an EA day, because under these circumstances, the municipality requires assistance from a neighboring station, and there'll be some extra cost attached to that. The question is, what's the probability that this will happen on more than 60 days in a given 365-day year? Solution. First thing we'll need to do is to find a way to count the number of EA days in a year. And we do this by defining random variables xi equal 1 if there are more than 3 fires on day I. We'll define such random variables xi as I runs from 1 up to 365. If xi is not 1, then it's 0. Of course, xi is determined by the number of fires on day I, n sub I, which we know to be a Poisson random variable with parameter, or with mean, 24 divided by 12, since there are 24 hours in a day, and the value of lambda is 1/12. In fact, the probability of an EA day on day I is the probability that there are 4 or more fires, which we can find by taking 1 minus the probability of 3 or fewer. The probability Ni is less than or equal to 3. Using the Poisson distribution, this is 1 minus the probability of 0, e to the minus 2, minus the probability of 1, that's 2 e to the minus 2, and minus the probability of 2 fires, that's 2 squared over 2 e to the minus 2, minus the probability of 3 fires, 2 cubed over 6 e to the minus 2, and it works out to 0.1429. So when we add up the random variables xi, 1 up to 365, that sum, by the way, has a binomial distribution with parameter 365 and p equals 0.1429. But it's also the sum of independent random variables xi. You can compute the expected value of xi, it's just the value of p. Similarly, each xi is binomial with n equals 1. It has variance p times 1 minus p. This gives us license to use the central limit theorem. To calculate the probability the sum of xi is bigger than 60, we standardize, subtract off the mean, n in this case 365, times p, and divide by its standard deviation, the square root of n times p times 1 minus p. We do that on both sides, and we end up with the probability that a standard normal exceeds 60 minus 365 times 0.1429, divided by the square root of 365, 0.1429 times 1 minus 0.1429. That's the probability that a standard normal is bigger than 1.1728. And looking this up in the normal table, we discover that probability is 0.1204. Continuity correction. This approximation, the normal approximation to this binomial probability, is okay, it's adequate, but we can improve on its accuracy. In fact, we can always improve on the accuracy of a continuous distribution approximating a discrete random variable, s in this case the sum of the xi's. Of course, a discrete random variable, like s, cannot be normally distributed. Let's display a probability histogram for a discrete random variable together with a continuous, for example, a normal approximation to it. In a probability histogram, the bar around the value, for example, 61, has area equal to the probability of that value. So if we're interested in the probability of the values 61, 62, 63, we should add together the area of these 3 bars in the probability histogram. But you'll notice, for example, that the bar representing the probability of 61 begins at 60.5 and runs to 61.5. So if we want the area, that's colored yellow in this graph, and we want to approximate it using the continuous curve, we should integrate the continuous curve not beginning at 61, but beginning at 60.5. That change in the boundary point by an amount 0.5 is referred to as a continuity correction. If I want the probability that s is 61 or greater, I should integrate the continuous function, not from 61, but from 60.5 on. In this case, take the area under the curve from 60.5 all the way up to 365.5. This is to say that we'll get a more accurate approximation of the probability that the sum of xi is bigger than 60 for a binomial random variable by finding the area under the corresponding normal curve from 60.5 all the way up to 365.5. Probably the easiest way to incorporate the continuity correction is to write the original problem, the probability that the sum is greater than or equal to 61 and less than or equal to 365, and then noting that that sum is discrete, move the boundary halfway to the next value on the left, over to 60.5, and halfway to the next value on the right, 365.5, and follow that up by then standardizing the random variable in the middle, of course doing exactly the same thing to the left and right sides. And only at the last stage do we replace it by a standard normal random variable z. This will turn out to give us a value like z is bigger than 1.2476, less than 46.864. You will, of course, have noticed that whether I use 46 on the right or infinity will make essentially no difference to the calculation of the probability. It's 0.1061. Now, this is quite a lot closer to the true value than is the value we obtained earlier, 0.1204, when we did not use the continuity correction. When do we need to use a continuity correction? Well, suppose, for example, we're interested in the probability of a single value. The probability s is equal to 61, where s may have a binomial distribution. Then, if we fail to use the continuity correction, and we approximate s by a continuous random variable, we standardize on both sides, and we end up with the probability z is equal to a given number. Of course, for a continuous random variable z, the probability is equal to any number is 0. So, failing to use the continuity correction here gives the answer 0. A poor approximation indeed. If I solve the same problem with the continuity correction, probability s is equal to 61, well, that, of course, is the area of the histogram bar for s between 60.5 and 61.5. So I replace it by s is between 60.5 and 61.5, standardize as before, and now we end up with the probability that a standard normal random variable z falls in a non-degenerate interval. That probability determined from the table to be 0.0249. The true value of this binomial probability I worked out, and it turns out to be 0.0242. Without the continuity correction, our approximation to this was 0. With it, it was 0.0249, very close, in fact, up to the fourth decimal point, to the true answer. In general, therefore, when we use a continuity correction, we move halfway to the next possible value of x, when a random variable has a discrete distribution. But if I'm approximating a continuous distribution by another continuous, like the normal, there is no need to go halfway. In fact, no adjustments necessary at all, since the next value is infinitesimally close. We'll suggest here that rather than you try to memorize when you should add or subtract 0.5, when you're approximating a discrete distribution, identify the histogram bars that should be included. Figure out where their endpoints lie, and make sure you've included the full span of each bar to be added in. And finally, as we've just seen, whenever you're approximating the probability of a single value for a discrete distribution, like the probability x equals 50 when x is discrete, you have to use a continuity correction. Otherwise, you'll end up with the answer 0. But again, this is only the case when you're using a continuous distribution to approximate a discrete. A normal approximation to the Poisson distribution. Suppose x is a random variable with a Poisson distribution, parameter mu. And suppose that parameter mu is large, 50, 70, 100. Remember that the expected value of a Poisson is its parameter, the value of its parameter, mu in this case, and the variance is also mu. And now imagine that mu is an integer. If I were to add mu-independent Poisson random variables, and they each had parameter 1, then we've seen before that the sum of those independent Poisson random variables with parameter 1 is Poisson with parameter mu. In other words, If x is Poisson with parameter mu and mu is large, I can write x as a sum of independent yi, mu of them, where each yi is independent and Poisson with parameter 1. When mu is large, this means that the central limit theorem must apply, because it's a partial sum of many independent random variables. And that in turn tells us that x must be close to being normally distributed. In conclusion, the central limit theorem tells us that if x has a Poisson distribution with parameter mu, and I look at the standardized random variable x minus mu over the square root of mu, that standardized random variable will approach a standard normal distribution as mu goes to infinity. Here's an example. Suppose I have a Poisson random variable with parameter mu. Let's approximate, using the normal approximation, the probability x is greater than mu. Compare this approximation with the true value when mu is equal to 9. Well, we've already seen that if mu is large, x minus mu over the square root of mu is approximately standard normal. You might ask whether 9 can be considered large, but we'll attempt the approximation in any case and see how accurate it is. The convergence of the cumulative distribution function for the random variable z sub mu tells us that the probability z sub mu is less than or equal to x will converge to the probability z is less than or equal to x, where z is normal 0, 1, as mu goes to infinity. Let's ignore the continuity correction for the moment. This means that the probability x is less than or equal to mu, I'm putting at little x equal mu, is the probability z sub mu is less than or equal to 0, which, if mu is large, is approximately the probability a standard normal is less than or equal to 0. And by the symmetry of the standard normal density, we know that's 1/2. Of course, the probability x is greater than mu also approaches 1/2. Let's see how that approximation works in the case mu equals 9. But this time we'll use the continuity correction. So the probability that x is strictly greater than 9 is the probability x is 10 or 11 or 12 and so on. If we start with 10, that histogram, bar for that probability histogram, begins at 9.5. The probability x is strictly bigger than 9 is the same as the probability x is greater than 9.5, the endpoint of that particular bar, which is the probability z sub mu is greater than 0.5 divided by 3. 3 is the square root of the variance, 9. Or the probability z is greater than 0.1667, where z is standard normal now, and from a normal table, we end up with 0.4338. Let's compare this with the true value. When mu is equal to 9, I can work that out. The probability x is bigger than 9 is 1 minus the probability it's less than or equal to 9. And all I need to do is add up those 10 possible values, 0, 1, up to 9. And when I do that, subtract from 1, I get 0.4126. Fairly close to the value which incorporated the continuity correction, 0.4338, but significantly farther from the value 1/2 or 0.5 we got when we failed to use a continuity correction. Here's a problem you should attempt on your own. A smartphone service desk handles repairs on smartphones, and 60% of them are easily repaired at a relatively small cost, say $30. 30% require more significant repairs. The cost in this case is approximately $80. 10% are beyond repair and must be replaced, and the cost for replacement is $300. Suppose the desk has 100 phones returned in a month. Find the approximate probability that the total cost of repairs will exceed $10,000. Solution. Begin by writing down the distribution for the cost of repairs. The cost for a single smartphone, called x sub I, has a distribution as follows. When little x equals 30, the probability of that is 0.6. When it's 80, the probability is 0.3. And when little x is 300, the probability of that is 0.1, 10%. And then we've calculated the expected cost and the variance. The expected cost is 72. The variance of the cost, well, the standard deviation of the cost, obtained by computing first e of x squared and then using the formula variance equals e of x squared minus the mean squared. The standard deviation turns out to be 79.22. So by the central limit theorem, when I add up 100 independent versions of xi, I get approximately a normal distribution with mean 100 times mu and variance 100 times sigma squared. 100 times mu is 7,200, and 100 times sigma squared, 627,600. So the probability that the sum of xi exceeds 10,000, standardizing on both sides, you'll notice because we're adding up a large number of random variables, I've ignored the continuity correction. Standardizing is the probability that a standard normal exceeds 10,000 minus 7,200 divided by the square root of 627,600, or the probability z is bigger than 3.53, where z is a standard normal random variable. Again, from normal tables, this is 1 minus 0.99979, or 0.00021, an exceedingly small number. There's virtually no chance that the cost will exceed 10,000, provided there are only 100 repairs to be made in the month.